Alright, so today we're looking at irreducible root systems. Irreducible root systems. So a root system phi is said to be irreducible if it cannot be partitioned into two sets such that they're both proper subsets and the union of both is the full set. Two sets such that each root in one set is orthogonal to each in the other. So essentially they're orthogonal pairwise. Oh, and that is not one word, and it's not spelled that way either. Notice that we state that phi is irreducible if and only if its base, a base of it, is irreducible in the same way. Now we need to prove this. First off, let phi be partitioned into phi1 and phi2. So the union of phi1 and phi2 has to be phi, and they have to be pairwise orthogonal, component-wise. Yeah, component-wise, not pairwise. Unless delta belongs to one of them, this induces a partition of our basis triangle. But if triangle is contained in one, say phi1, then the bracket of our base with the other one, say phi2, now has to be 0. But since delta spans E, we then have that E is as a whole orthogonal to phi2. So conversely, let phi be irreducible, but let our base be reducing into delta 1 and delta 2 in the same manner. So the union of these two is all delta, and they are orthogonal component-wise. As each root is conjugate to a simple root, if phi I is the set of roots with a conjugate in delta I, then phi is the union of phi 1 and phi 2. So recall that if A and B are roots with the form of 0, orthogonal, then their reflections commute. And since the file group is generated by the reflections of elements in the base, yeah. Each root in each phi I is from 1 in delta I by adding or subtracting elements in I and delta I. I think we've seen that before as a lemma or something. Maybe not, but yeah. Thus phi I lies in the subspace EI of E spanned by delta I, so that the phi 1 and phi 2 are orthogonal. So one of the phi i's is empty, so the corresponding delta I must be as well. And this comes with the... Now we move on to a lemma. Let phi be irreducible. There is a unique maximal root beta with respect to our ordering. Our partial order from before. If some beta, if we write beta as the sum of k alpha alpha for alpha in our base, then all of our coefficients k alpha must be strictly positive. And so the proof. let beta be the sum of K alpha alpha for alpha in our base, be maximal. Since there's only so far we can push a root in a given direction, this is going clearly a maximal element. Is it just unique is the question. This is obviously going to be positive. If we're going to set delta 1 to be the elements of our base, where K alpha is positive. And we're going to set delta 2 to be the elements of our base with a 0 coefficient in K alpha. Because we know we're not, then, I'm sorry. We know we're not going to have any negative elements as a coefficients, because then we could just swap them around. So then we have that delta 1 and delta 2 form a partition of delta. But we know that delta is irreducible. Suppose that delta 2 is non-empty. Then we have that the bracket of any root alpha with beta must be non-positive for any alpha in our delta 2. And since phi is irreducible, there must be an alpha of our delta 2 non-orthogonal to delta 1. So that the bracket of alpha and alpha prime is negative for some alpha prime in delta 1. So the inner product of alpha and beta must be negative. Thus, beta plus alpha is a root. So beta is not maximal. But we know it's maximal, so delta 2 is empty. So delta 2 is empty. So K alpha is positive for all alpha in our base. And we also see from this that the inner product of alpha and beta is non-negative for all alpha in our root, in our base. Now let beta prime be another maximal root. Again, so we notice that beta and thus beta prime must have a root alpha with the inner product being strictly positive. Thus, the inner product of beta and beta prime is strictly positive. Well, let's beta prime and beta is strictly positive. And so beta minus beta prime is a root. Unless beta is beta prime. But if beta minus beta prime is a root, then one of them has to be bigger than the other. So as we cannot have one beta being bigger than the other, beta prime is beta, and so it is unique. Alright, let's go to our second lemma here. Let our root system be irreducible. Then the vial group acts irreducibly on E. With the vial orbit of any root alpha spanning E. And the proof. The span of the vial orbit of a root is a non-zero vial invariant subspace of E so the first half implies a second. First half of the lemma, that is. So, let E prime be probably we're going to assume non-zero subspace. Yeah, we're going to assume non-zero. Non-zero subspace of E invariant under the vial group. And so now we want to show that the action of the vial group is irreducible, so we want to show that E prime is then all of E. Then the orthogonal complement, E double prime of E prime is also going to be vial invariant. With our space E decomposing into E, the direct sum of E prime and E double prime. Thus, for alpha in phi, either alpha lies in E, or E prime is contained in the orthogonal hyperplane of alpha, since the reflection of E prime under alpha is going to be E by an exercise, which we're not going to do on this video. Thus, alpha lies in E. Thus, if alpha doesn't lie in E prime, we have that it lies within E double prime. So each root lies in exactly one of E prime and E double prime. Thus we have a partition, of our root system into orthogonal subsets. So one must be empty. As phi spans E, our E prime must be just all of E. And there's two more lemmas we have to go here. The first one is we're going to let our root system phi be irreducible. Then we see that at most 2 root lengths occur in phi and all roots of a given length are conjugate under the Weyl group. For 2 roots, alpha and beta, not all the wording here is weird, but not every reflection generated by one root can be orthogonal to a given root beta, since the no, I get it. For arbitrary sigma in the Weyl group, since we saw that the image of alpha under all of the Weyl group spans E if their form is not 0, and the possible ratio of square root lengths possible ratios of squared root lengths, not square root of lengths, it's square of the root length of alpha and beta are 1, 2, 3, 1/2, and 1/3. And thus, our first statement as you can see that taking 3 root lengths yields a ratio of 3/2. Now let alpha and beta be equal length. You want to show the conjugate, I'm guessing? Replace one with a vowel conjugate such that they are non-orthogonal and distinct, obviously. Thus, by our previous chart, we have that the angle bracket of alpha and beta, and equally the angle bracket of beta and alpha, is going to be positive or negative 1. Replacing beta with negative beta in the negative case. Which of course is the image of beta under sigma beta. So we can assume that the angle bracket of alpha and beta is 1. Then the conjugate of the composition of sigma alpha, sigma beta, sigma alpha of beta, sigma alpha, sigma beta, beta minus alpha is sigma alpha minus beta minus alpha plus beta, which is sigma alpha of negative alpha, which is alpha. Alright, and so when we're working in an irreducible root system, when sigma is irreducible, we may call roots long or short. If they're all the same length, it doesn't really matter. It's conventional to call them all long, I guess. Now come to another lemma. Let sigma be irreducible with 2 distinct root lengths. Then the maximal root beta, which we saw before, is long. And the proof. For alpha in phi, we will show that the form of beta on itself is at least a form of alpha on itself. So we may replace alpha with a vial conjugate in the closure I'll just write it out. The closure of the fundamental vial chamber of our base. Since then beta minus alpha is going to be positive, for all sigma in the closure of the vial chamber of our basis, the fundamental vial chamber of our basis, we have that the form of sigma with beta minus alpha is non-negative. Then by the cases where gamma is beta and where gamma is alpha, we have that the form of beta with itself is at least the form of beta with alpha, which is at least the form of alpha with itself. And that's the end of the chapter. I don't know, should we carry on to the next one? It'll double the length of this video, and it's already like half an hour. I think we will call it here for now, at least. I'm trying to skim through. I don't know exactly like how Humphreys divides its sections. I'll have to look into that later. But yeah, we'll call it here for now.